In a bed of volcanic ash in northeastern Nebraska, laid down a little under 12 million years ago, lie the skeletons of more than 100 rhinoceroses. They are still in the positions they died in, gathered around what was then a waterhole, and they are not alone in it. There are horses in that ash, and camels, and a range of smaller animals, all of them belonging to a warm grassland that covered the middle of the continent at a time when the Rocky Mountains were already old. The order in which they died can be read. The smaller animals went first, within days of the ash arriving. The rhinoceroses, being the largest and the slowest to be overwhelmed, lasted longest, several weeks, judging by their own bones, which had begun to change during the interval. When a large animal's lungs fail slowly enough, the skeleton responds. New bone grows on the outside of the old bone in thin, irregular sheets, and that growth takes time. It is, in effect, a clock. Those animals recorded the length of their own dying in a material that has now outlasted the grassland, the water, and the volcano. The ash came from about 1,000 kilometers to the west, from a volcanic center in what is now southern Idaho. The old calderas are still there, worn down and largely unvisited. What made them has moved on, or more accurately, the continent has moved, sliding slowly southwest across a hot region of the mantle that has stayed roughly where it was, so that the record on the surface reads as a track. A line of spent craters running northeast across Idaho, each one younger than the one before it. The youngest end of that line sits under the northwest corner of Wyoming. It is called Yellowstone. The system there has produced 3 eruptions on that scale in a little over 2 million years, and the most recent of them, roughly 630,000 years ago, left the hollow that most of the park now sits inside. The caldera is about 70 kilometers across at its widest. It is too large to perceive from within, which is part of the reason nobody identified it as a volcano until the late 1960s, when a geologist mapping the plateau on foot began to notice that the cliffs kept facing the same direction, inward. The standard account of what would happen if that system erupted again is mostly an account of the crater. Flows of hot gas and rock moving faster than anything alive can get out of the way. The park itself gone inside a day. Several hundred kilometers of the northern Rockies made uninhabitable before the first evening. That account is roughly right. It is also, from the perspective of most of the continent, the short part. The animals in Nebraska were 1,000 kilometers from the eruption that killed them, and they had weeks. What reached them was weather. Fine grey ash falling out of a high cloud, settling on the grass, settling into the water, going into the lungs of everything that breathed near it. Nothing about the afternoon it began would have looked like an emergency. The grass was still standing and the water was still drinkable, so the herds kept coming to it and kept breathing near it, and somewhere in the weeks that followed, it finished them. That is the genuinely difficult part of an eruption at this size, and it is the part a minute-by-minute account tends to move past quickly, because minutes stop being the useful unit somewhere around the end of the first week. After the largest of these events, the upper atmosphere holds fine material across most of a hemisphere for a long time, and sunlight thins, not to darkness, but to something closer to a long overcast that does not clear on any schedule a living thing can wait out. Everything that feeds on light feeds a little less, and everything that feeds on those things feeds less than that, down the whole length of the chain. If this is the kind of thing you want more of, subscribing helps a channel like this one more than almost anything else does. And there's one question worth leaving in the comments, if you feel like it. The odds of a Yellowstone eruption in any given year come out at roughly 1 in 100,000. When you hear a number that small, does it make the thing feel further away or closer? Now, if you're comfortable, get a little more comfortable. The lamp nearest you is almost certainly brighter than it needs to be, and nothing here needs you awake for it. The ground we're going to is quiet at the moment, in the sense that nothing has erupted out of it in a very long time, and it is also, at this moment, venting heat through more geysers and hot springs than exist anywhere else on the planet. There are something like 10,000 hot springs, mud pots, steam vents and geysers inside the park, and every one of them is a symptom of the same thing. Water that has worked its way down through fractured rock, come close to something hot and been sent back up. The water itself is ordinary. Rain and snow melt old by the time it returns. Decades at least, and in places a good deal more than that. What matters is what it touched on the way around. The first kilometre or so below the basins is broken volcanic rock with water moving through every crack in it, which is why the ground in the thermal areas stays warm enough that snow won't sit on it. Below that, the water gets hotter and scarcer, and lower still it stops entirely, and somewhere between 4 and 8 kilometres down there is rock that has been hot enough for long enough that a fraction of it has melted. A fraction. This is the first thing that has to be corrected about magma, because the word suggests an underground lake, and what is actually down there is closer to wet gravel. The solid grains are crystals, feldspar and quartz, the ordinary minerals that come out of a cooling melt first, and the liquid is what's left over, filling the spaces between them. Recent imaging puts the liquid fraction beneath Yellowstone somewhere between 9 and 20%, depending on which body you're looking at and which method you use to look. That range comes from two entirely separate approaches, which is the reason to trust it. One group worked with seismic waves, measuring how much the ground slows a passing vibration, and found the largest slowdown between 3 and 8 kilometers, the same depth range where the rhyolite of the previous eruptions is thought to have assembled. Another, led out of the US Geological Survey, used the Earth's own electrical fields on the principle that molten rock conducts electricity far better than solid rock does, and mapped at least 7 separate pockets of the stuff, from 4 kilometers down to nearly 50. One of those pockets, northeast of the caldera, holds something like 440 cubic kilometers of liquid on its own, which is a substantial share of everything that came out in the last caldera eruption, and which is also going absolutely nowhere because it is distributed through solid rock the way water is distributed through a sponge. The threshold for eruption sits somewhere above 50% melt. Below that line, the crystals are in contact with each other and carry the load themselves, so the whole mass has strength. It deforms slowly under pressure rather than flowing, in the way that wet sand holds a shape. Above the line, the crystals lose contact and float, the liquid takes over, and the material can finally go somewhere. Yellowstone is not near that line, and has not been near it for a very long time. What makes this particular magma worth paying attention to anyway is that it manufactures its own explosive, and it does so by cooling. Rhyolite is the high silica end of the family, thick and slow and reluctant to move, and it carries a surprising quantity of dissolved gas, water above all, along with carbon dioxide, chlorine and sulfur. Glass droplets trapped inside crystals from earlier Yellowstone eruptions have come out at 2 to 3% water by weight, which sounds like nothing until you register that it is water dissolved inside rock, held there by the pressure of everything stacked above it. The trap is in the crystallization. When feldspar and quartz come out of the melt, they take silicon and aluminum and oxygen with them, and they leave the water and the sulfur behind. The liquid that remains is therefore a smaller volume, carrying the same dissolved load, which means it grows richer in gas with every year that it cools. Nothing is being added. The charge builds because the magma is slowly freezing, and freezing concentrates what it cannot use. Left alone, that process has an endpoint. The melt eventually holds more gas than the pressure can keep dissolved, Bubbles come out of solution. The bubbles occupy far more room than the liquid they came from, and the body begins to push on its own roof. It is not left alone. In 2025, a team from Rice University, working with colleagues from Utah, New Mexico, and Texas, drove a truck weighing some 26 tons into the park, set it down, and shook the ground with it, a controlled vibration repeated with instruments listening for what came back. They were looking for a boundary, and they found one at about 3.8 kilometers down. That is not a great depth. If there were a road, it would be a few minutes' drive. What sits at that boundary is a cap, a layer where gas rising out of the magma below has collected in the pore spaces and fractures of the rock, bubbles held inside a solid framework. The result worth publishing was that the cap is not sealed. Gas moves through it continuously, along cracks and around the edges of mineral grains, working upward into the hydrothermal system and out through the ground in the basins. Brandon Schmant, one of the researchers involved, described the system as doing steady breathing, bubbles rising and releasing over and over at a rate that keeps the pressure underneath from building toward anything. Which means that if you are standing on a boardwalk in the Upper Geyser Basin on an ordinary afternoon, watching steam come off the water in the cold air, the pressure release is happening in front of you. That is what the steam is. The geysers are not scenery that happens to sit on top of a volcano. They are the mechanism by which the volcano is, at present, not going off. There is a version of this that sounds like reassurance, and to a considerable extent, it is one. The melt is too dispersed to move by two methods that share nothing but the ground they were pointed at. The gas is leaving roughly as fast as it accumulates. The last lava to come out of the caldera did so around 70,000 years ago, and everything measurable since then describes a system holding a great deal of heat and letting it out slowly, which is what it appears to have been doing for most of that interval. A valve, though, is a description of what a system is doing at the moment. It is not a statement about the system's intentions. Every one of those worn-down calderas along the track through Idaho was also, on some particular afternoon, venting steadily and sitting well below its threshold and behaving exactly like this one. And the changeover, when it came, did not run on geological time. That is the part that is genuinely hard to hold in the head. 70,000 years of a system doing the same patient thing, and then a transition measured in days. Gualda and Sutton were working on quartz from a different volcano, crystals a millimeter or two across, picked out of pumice from the Bishop Tuff in eastern California, which is not Yellowstone, but is the same kind of magma behaving the same way, and which has been studied in more detail than almost any deposit of its kind. The Bishop eruption emptied several hundred cubic kilometers about 750,000 years ago, left a caldera that Highway 395 now runs across, and appears to have done the bulk of its work in 3 to 6 days. What the two of them wanted out of the crystals was a clock. Quartz grows in layers, and the layers are not chemically identical. Titanium substitutes into the crystal structure at a rate that depends on conditions at the moment of growth. So a crystal that formed while conditions were changing comes out banded, with the bands in order. Under an electron beam, those zones glow at different brightnesses, which makes them visible. Inside a synchrotron, a machine that produces an X-ray beam narrow and bright enough to map chemistry point by point, the titanium itself can be measured across a single grain. The last step is the one that turns a picture into a date. Titanium migrates through quartz slowly, the way ink spreads through damp paper, so the boundary between one growth zone and the next begins sharp and blurs with age. Measure the blur and the age falls out of it. The outermost layer on the Bishop crystals, the rim, the final thing to grow before the magma left the ground, came back sharp. 70% of the rims had formed inside the last year. Individual grains ranged from about 35 years down to roughly a minute, which is its own kind of information, but the middle of the distribution sat at 4 days. Those rims are thin in a way that is difficult to convey. The crystals were adding material at something on the order of 10,000ths of a millimeter a day, so 4 days of growth comes to a band about half the width of a human hair. The entire final approach to one of the largest eruptions in the geological record fits inside a layer that cannot be seen without a microscope aimed at it deliberately. What made the quartz grow at all is the part that carries the chapter. Silica stays dissolved in rhyolite in proportions that depend on how much water the melt is holding, and the melt holds water in proportion to the pressure on it. Take the pressure off, and water comes out of solution. Take water out of the melt, and the melt can no longer keep its silica dissolved either, so quartz begins to crystallize. Every micrometer of that outer band therefore corresponds to pressure coming off a body of magma that had begun at last to move. Of all the numbers in this subject, that is the one that refuses to sit quietly, harder to set down than the volumes, harder than the temperatures, which get large enough to stop meaning anything. 4 days is a length of time a person can hold in mind without effort. It is a long weekend. It also fits with something the imaging work has been arriving at from a different direction, which is that the eruptible state is a transient. A crystal mush can sit in the crust for 100,000 years or more without ever being capable of movement. The layers that can move, melt rich enough to lose their rigidity, seem to assemble near the top of the mush and last a few thousand years at the outside, which is a large part of why nobody has ever caught a system of this size sitting in that condition. The condition does not sit, so the 4 days are the end of a much longer assembly, and they are also the only stretch of the sequence anyone has read at anything like this resolution. What can be said about them at Yellowstone specifically is a reconstruction put together from crystals like those, from the deposits of eruptions that have already happened, and from the behavior of gas inside rock when the weight above it comes off. Nobody has ever instrumented one. The order of events is not seriously in dispute. It begins with the pressure dropping, perhaps because the rock above a melt-rich layer finally gives, perhaps because the layer's own buoyancy has quietly exceeded the strength of its roof, and the honest position is that the distinction matters enormously and cannot currently be made. Whatever opens it, the water that has been concentrating in that melt for as long as it has been cooling stops being able to stay dissolved and starts coming out as bubbles. Bubbles take up vastly more room than the same water did in solution. The column expands, and expansion pushes it upward, and moving upward puts it under less pressure still, which brings more water out of solution, which makes more bubbles, which expands it further. This is a loop, and it is worth naming as one because loops are where events of this kind stop being events and become runaways. Nothing external is driving it after the first push. The magma is now accelerating itself, and each stage of the acceleration produces the conditions for the next. Through the first 2 days, the movement is not dramatic by any measure a person standing above it would recognize. Ground shifts, water in the hydrothermal system starts behaving oddly as the plumbing beneath it deforms, and the seismic record fills with small events at depths that have not produced small events in living memory. Underneath, the column is reorganizing. By the 3rd day, the gas fraction has climbed past the point where the melt is the continuous substance in the mixture. Somewhere in the conduit, the bubbles come to occupy most of the volume. The thin films of liquid between them are being stretched faster than liquid can stretch, and they break. Above that level, the material stops being rock with gas in it and becomes gas with shattered rock in it, compressible, far less dense, and no longer subject to any of the constraints that had been slowing it down. By the 4th day, the column has sorted itself into three parts. Melt at the bottom, still recognizably molten rock, a level in the middle where the liquid stops being continuous, and above that, a rising mixture of gas and glass fragments traveling faster than anything this system has done in 70,000 years. Between that mixture and the open air, there is a few kilometers of ordinary rock. What remains at that point is arithmetic. The mixture is accelerating. The rock above it is a fixed thickness, and removing that thickness will take some number of minutes. What the rising mixture meets in the last kilometer is water. The ground above a system like this one is soaked in it. The same water that has been feeding the geyser basins for as long as there have been geyser basins, sitting in fractured rock at temperatures well above boiling and kept liquid by nothing except the weight of everything stacked on top of it. When the conduit arrives underneath that layer and the weight comes off, the water flashes. Liquid water turning to steam expands by well over 1,000 times, so the opening move at the surface belongs to the groundwater rather than the magma, and it is violent out of all proportion to the amount of magma involved. The eruption that produced Lake Taupo in New Zealand began this way, with wet explosions running through several phases before the dry column established itself, and the work those explosions do is excavation. They clear the ground, they decide where the vent is going to be. Then the vent opens properly, and what comes out is the mixture from the conduit, gas with shattered rock suspended in it, mostly gas by volume, arriving still under pressure and expanding as it clears the ground. It is worth saying plainly how thin the observational record becomes at this point. Nobody has watched a caldera-forming eruption. The largest eruption ever measured with instruments was Pinatubo in the Philippines in 1991, and Pinatubo was on the order of 100 times smaller than what is being described here, and 1,000 times smaller than the largest event this system has produced. Everything from the vent upward is reconstruction, deposits mapped in the field, laboratory work on how gas-charged rock behaves when the pressure comes off it, and models built to reproduce eruptions that were observed, then run at settings that were not. The physics is solid. The eyewitness account does not exist and is not going to. 30 kilometers from the vent, a distance that is still comfortably inside the park, the order in which the event arrives has nothing to do with the eruption and everything to do with the media it travels through. The ground goes first. Seismic waves move through rock at something like 5 kilometers a second, so the shaking would begin about 6 seconds in, and it would not be the kind of shaking that invites interpretation. Light arrives in no time worth counting, so whatever stands above the vent would be visible immediately after that. Sound covers roughly 1/3 of a kilometer a second, which puts the first noise at about 90 seconds. For a minute and a half then, it would be happening in front of anyone looking at it in silence. What would be visible in that interval is a column already several kilometers up and still climbing, widening as it rises. There is no comparison available for it in ordinary experience because the objects people use to calibrate the sky, cloud, mountain, storm, all top out well below where this one is going. It is taller than weather. Underneath, the vent is enlarging. The mixture leaving the ground is abrasive and moving fast, and it takes the walls with it, so the opening widens through the first minutes. A wider opening offers less resistance. Less resistance means more throughput, and more throughput widens it further. Whatever the vent was when it opened, it is not that anymore by the end of the first hour. At the same time, the level at which the magma fragments is migrating downward. As the conduit empties, the pressure at every depth inside it falls, and the depth where the bubbles finally win moves deeper into the system. The eruption is not drawing from a fixed reservoir through a fixed pipe. It is eating downward into itself, and the deeper it eats, the more of the reservoir becomes available to it. Where this arrives, in an eruption of this class, is a throughput somewhere above 200 million kilograms every second. That figure is hard to keep hold of in the abstract. It comes to 200,000 tons of rock and gas leaving the ground per second, which means that in the time it takes to read this sentence aloud, the vent has removed something on the order of 1 million tons of Wyoming. The column above it is being built out of that. Material leaves the vent as a jet, driven by its own expansion, and for the first few kilometers, momentum is doing all the work. Above that, the jet has slowed, and it keeps rising only because it has been dragging cold air into itself the whole way up, heating that air and becoming lighter than the atmosphere it is displacing. The column is buoyant. It floats in the way a hot air balloon floats. On air it has warmed itself. A structure that tall clears the horizon from a very long way off. It would stand in the sky over most of Montana and Idaho, over Salt Lake City, over the eastern edge of Oregon, within the hour. A shape on the northern or southern horizon, depending on where the observer happened to be standing, unhurried, gaining height in a way too slow to see. From several hundred kilometers away, it would appear to be standing perfectly still. Columns of that height do not last, and what ends them is the same thing that built them. A column stays up by mixing cold air into itself until it weighs less than the air around it. That mixing happens at the edges, where atmosphere is dragged across the boundary and pulled inward, and the amount of edge available does not grow nearly as fast as the amount of material being forced through it. A modest column has a great deal of surface relative to its volume and turns buoyant without difficulty. A very large one is mostly interior, and the interior is a long way from any air. There is therefore a throughput above which the arrangement simply fails, and an eruption of this class spends its first hours walking straight toward that number. The vent has been widening since the beginning, which slows the exit velocity across any given patch of the opening and makes the mixing less efficient. The system has been eating downward, which brings up material that is denser and carries more crystals than what came first. Both effects push the same way, and somewhere past a throughput of 200 million kilograms a second, the core of the column stops managing to become buoyant at all. The eruption does not pause when this happens. Material keeps leaving the ground at the same rate or faster. It just stops going up. A column that has lost its buoyancy fails from the middle outward. The core is the densest part and the part furthest from any supply of air, so it gives out first and falls back around the vent, and it reaches the ground, still holding most of the energy it left with. 10 or 15 kilometers of falling adds a good deal to a mixture that was already moving quickly when it started. What spreads from the base of that collapse is a density current, the same class of thing as cold air sliding down a hillside after dark, or the fog that pours off a block of dry ice and runs along a tabletop. It is heavier than the air it sits in, so gravity pushes it outward along the ground rather than upward, and it keeps traveling for as long as it stays heavier than its surroundings. These currents are layered, and the layering turns out to matter more than almost anything else about them. The base is dense and loaded with rock, grinding along the surface, moving blocks. Above it rides a thinner, hotter, far more turbulent cloud of fine ash and gas, and that upper part is the faster of the two. Where the dense base is stopped by a ridge, the dilute cloud goes over the top and carries on down the other side. Almost everywhere these events have been examined afterward, the outer edge of the destruction was drawn by the thin part rather than the thick one. The upper limit for flows of this kind is somewhere around 700 kilometers an hour. 10 kilometers of ground disappears in under a minute at that rate, and the current spends the entire distance inside its own dust, so it does not approach in the way an object approaches. It arrives as a change in the air. There is a line below which a hazard is something a person can respond to, and above which it is only something that happens to them. This sits well above that line. If you were 10 kilometers out with a vehicle on clear road, having spent the whole morning expecting precisely this, you would still be in the wrong place because the interval between seeing it and being inside it is shorter than the interval between deciding and moving. That is the entire content of the situation, and it is a strangely flat thing to write down. There is no decision available, and so there is no story. The killing is done by heat and by breathing. The interiors of these currents run at several hundred degrees, and air at that temperature damages the lining of the airway on contact, which means the mechanism needs nothing dramatic to work with. Where the dense base passes, buildings and forest go with it. Out at the margins, where only the thin cloud reaches and the heavy material has already come to rest, the damage can be almost entirely thermal and almost entirely internal. How far any of this would reach at Yellowstone in particular is not something anyone has published a proper model for. There is no flow simulation for specific future vents in that caldera of the sort that exists for smaller, busier, better instrumented volcanoes, partly because nobody knows where the vents would be, and partly because an event this rare does not attract that kind of modelling effort. What exists instead is the deposit, which is a cruder instrument and a more reliable one. The Lava Creek eruption spread its pyroclastic material across roughly 7,500 square kilometers. Yellowstone National Park covers about 9,000. The flows from the most recent caldera-forming eruption at this system, in other words, ended up occupying rather less ground than the park does today. The Huckleberry Ridge eruption 2 million years before it, better than twice the volume, put its flows across something over 15,000 square kilometers, which comes out, if the shape had been a circle, which it was not, at about 70 kilometers in every direction from the source. Neither footprint is circular, because currents like these are governed almost entirely by the ground they cross. They run down drainages, pool in basins, thin as they climb, and pick up speed again on the far side of whatever they have just climbed. The Yellowstone Plateau stands high, and the country around it does not stand high evenly, so the reach in some directions would be far greater than in others, and the honest summary is that the map would be settled on the day by the vent position and the shape of the valleys. What can be said without any model at all is the accounting. Over a few days, a volume of rock and gas that had spent the previous 600,000 years underneath Wyoming would come to be lying on top of it instead. As flow deposits across the plateau, as ash across the continent, as fine material carried into the stratosphere and no longer belonging to any particular place. Geologists would eventually measure it by drilling into it, and the space it came out of would still be down there, several kilometers below the surface, with the full weight of the plateau resting on a roof that no longer had anything underneath it. Inside the ring, the tuff laid down by a single eruption can run a kilometer thick, while the same tuff from the same eruption, a few kilometers outside the ring, comes to a matter of tens of meters. It is the same rock, put down over the same few days by the same flows. The only difference between the two places is that one of them was going down at the time, where erosion has cut deep enough into an old caldera to expose its edge. You can walk across that boundary in a few minutes, the outflow sheet on one side, thin and dipping gently away from the center, and on the other, a pile of identical material 100 times deeper, which went into a hole about as fast as the hole opened. That contrast is the collapse, recorded by the collapse. Nothing else produces it. The hole opens along a fault, and the fault is not the sort most people picture when they hear the word. It does not gape. It is a reverse fault, which means the two rock faces are pressed together as they slide rather than pulled apart, and it begins down at the margin of the magma body and grows upward through the crust until it reaches daylight. Though where the roof is thin enough relative to what lies beneath it, the fracture propagates downward as well as up. What the completed fault defines is a cylinder, a block of the Earth's surface, bounded on every side, with nothing left underneath it. At Yellowstone, that block would run roughly 70 kilometers along its long axis and 55 across the short one, and the fault enclosing it would amount to something on the order of 200 kilometers of continuous sliding surface. The whole of it moves together, or near enough to together that the distinction stops carrying any meaning. What happens along that surface while it moves is the part that turns a subsidence into a collapse. Rock grinding against rock produces heat, and the heat produced by a block of this mass moving at any appreciable rate is not a modest quantity. It is enough to melt a thin film of the rock along the fault itself. A film of melt is a lubricant. Friction falls, the block accelerates, the acceleration generates more heat, and more heat makes more melt. The fault greases itself with the rock it is destroying, and the further it goes, the less capable it becomes of stopping. How the block actually comes down depends on a ratio between two numbers, the thickness of the roof and the width of the magma body beneath it. The roof aspect ratio, as it is called, does most of the work in deciding what kind of caldera results. Where the roof is thin compared with the width of what sits under it, the surface bends rather than breaks. A broad, shallow sag, with any fault forming late or never quite reaching the top. Where the ratio is moderate, the block descends as a unit along a well-defined ring, dropping the way a piston drops in a cylinder, which is the classic picture and the one most diagrams show. And where the roof is thick relative to the chamber, the fault may never reach the surface at all. The roof founders from below, sinking as an arch into the space beneath it, with the surface expression arriving late and incompletely. Which of these Yellowstone would do is not known, and the reason it is not known is more interesting than an ordinary shortage of data. All three descriptions assume a chamber, one body of magma with a roof over it and a width worth measuring. The imaging of the last few years describes nothing of the kind. It describes at least 7 separate magma-rich regions between 4 kilometers depth and nearly 50, some feeding into each other and some apparently independent, distributed through the crust rather than pooled in it. A roof aspect ratio needs a roof and a chamber to be the ratio of, and it is not clear that Yellowstone possesses either in the form the models are built around. The deposits point the same way. Detailed work on the Huckleberry Ridge Tuff, the oldest of the three and by a wide margin the largest, has concluded that it came from the evacuation of multiple magmatic systems rather than a single one, in an eruption that proceeded episodically with genuine pauses in it. Its 3 members span something like 20,000 years, and the Earth's magnetic field reversed partway through the sequence, which is part of how the members can be distinguished from one another at all. So the collapse in a scenario like this one is unlikely to be a single clean subsidence along a single clean ring. Several overlapping subsidences, out of step with each other, parts of the floor dropping while other parts hold. The fault system working out its geometry as it goes. That is the more probable shape, and there is no way to specify it in advance. By the standards of everything that came before it, the collapse is a quiet event. The eruption does not conclude with a final detonation. It ends because the roof settles onto what remains of the reservoir and seals it, and because there is no longer enough gas-charged melt within reach of any vent to hold up a column. Output tails off across hours and days. The flows stop arriving. The column, with nothing feeding it anymore, drifts downwind as a spreading sheet and stops being a column. What remains standing at the end is a hole with a nearly flat floor, tens of kilometers across, filled with its own cooling deposits and steaming wherever groundwater has started finding its way back into rock that is far too hot for it. The plateau that used to be there is lower now by an amount measured in hundreds of meters and buried under a great deal of itself. The reconstruction runs out around here because what follows on the plateau is largely a matter of rock cooling, which it will go on doing for a very long time without much incident. What would not run out is the question that every hearing and every inquiry and every report written in the following decade would return to, and that question belongs to a stretch of time before any of this. 4 days is what the crystals record. The ground would have been saying something for considerably longer than that. Everything up to this point has been built on an assumption that the monitoring record does not support. The scenario ran cold. The 4 days began. The ground opened, and nobody standing on it had been given anything in advance, which is the version the question implies, and the version nearly every account of a supervolcano adopts because it is the version with a shape to it. The evidence points somewhere else. It also, having pointed somewhere else, declines to be reassuring about where it has pointed. Yellowstone carries one of the densest monitoring networks ever assembled around a volcano. Seismometers across the plateau and beyond it. Continuous satellite positioning stations that fix their own locations to within a few millimeters and report constantly. Radar from orbit that maps the movement of the whole caldera in a single pass, so that a centimeter of change over an area 70 kilometers wide is not merely detectable, but routine. Gas sampling, water chemistry, temperature loggers sitting in the thermal features. Somebody is looking at all of it every day. What that network would be expected to see ahead of a caldera-forming eruption is not subtle in the literature. Sustained earthquake swarms, not the ordinary background which at Yellowstone is busy, but swarms that persist, shallow, and migrate. Deformation running at centimeters per month instead of centimeters per year. Shifts in the volume and composition of gas leaving the ground. Most published assessments put the detectable window at weeks to months. A good many put it at years. The difficulty is that Yellowstone produces signals answering to that general description without any provocation whatsoever, and has been doing so for as long as anyone has been watching it. Between 2004 and 2006, the floor of the caldera rose 17 centimeters, at rates reaching 7 centimeters a year. The fastest sustained uplift measured there since measurement began, and unusual enough that the paper documenting it put the word extraordinary in its title. It was covered widely. A fair amount of that coverage interpreted it as precisely the thing this chapter is about. Then it slowed, and then it stopped, and then it reversed. In November 2013, the ground at Norris Geyser Basin, near the caldera's northwestern edge, went up at better than 15 centimeters a year, which is among the fastest rates ever recorded anywhere in the park. Nothing came of that either. And through the mid-2000s, while the caldera as a whole was rising, Norris was going down, the two areas moving in opposite directions simultaneously, which is a useful corrective to the idea that there is a single number called the ground level worth keeping an eye on. Since 2015, the caldera has been subsiding steadily at 2 to 3 centimeters a year. There is one interruption in that, and it repeats. Beginning around May or June each year and running through to September or October, the subsidence pauses and in some years reverses into half a centimeter or so of uplift before resuming its downward trend. That is snowmelt, groundwater recharging through the fractured rock, and the plateau flexing very slightly under the weight of its own wet season. The instruments installed to watch for a supervolcano are sensitive enough to watch the summer arrive, which brings the actual problem into focus. The network is not short of signals. It is short of any way to tell which of them mean anything, and the reason is arithmetic rather than engineering. Instrumental monitoring at Yellowstone goes back a century at the outside and a few decades in any form that would recognize what it was looking at. The interval between the last two caldera-forming eruptions was about 660,000 years. The record available for learning what the approach to one of these looks like covers something on the order of a 10,000th of the gap it is being asked to characterize, and it contains no eruptions at all. There is a smaller demonstration of the same difficulty, and it happened recently enough that people filmed it. On the 23rd of July 2024, Black Diamond Pool in Biscuit Basin, a few kilometers from Old Faithful, inside one of the most closely watched volcanic areas on Earth, went off. Water, mud and rock rose about 180 meters. The boardwalk was wrecked. Visitors ran and were fortunate. Nothing in the monitoring network had registered anything that morning to distinguish it from any other morning, and the same pool did it again afterward. That was a small event by the standards of this discussion, driven by hot water rather than magma, and the two processes are genuinely different. It remains a clean illustration of the distance between having instruments and having warning. So the 4 days recorded in the crystals and the years described in the monitoring literature are both true, and they are answers to different questions. The years describe the loading, melt gathering somewhere in the mush until a body of it becomes mobile, the roof above it weakening, the surface responding to all of that in ways that are measurable and, while they are happening, ambiguous. The 4 days describe the firing. The honest position on how those two connect is that nobody knows, because the only system ever observed doing the second thing was observed in retrospect, in the chemistry of quartz, several 100,000 years after it had finished. That leaves the question in an awkward condition. Could Yellowstone erupt tomorrow? Almost certainly not, in the sense that the loading has not happened. The melt is dispersed, the gas is venting, and the ground is going down. Could an eruption arrive without anyone having correctly understood what they were watching? That is a different question, and it is the less comfortable one because it does not depend on the volcano. It depends on whether the pattern that precedes an eruption can be told apart at the time from the pattern that precedes nothing, and there is no example of the first kind on record to hold the second kind against. You are, at the moment you hear this, living inside a stretch of that record. The instruments are running tonight. The caldera is going down by a couple of centimeters a year, and it will pause again in June. Whatever else that is, it is what the data look like while nothing is happening, and it is also the only baseline anybody has. There is one further thing to say about warning, which is that it applies to almost nobody. Inside the reach of the flows, notice changes nothing. The physics leaves no decision to be made with it. Everyone else on the continent is in an entirely different position, and their position is not settled by the ground at all. It is settled by where the cloud goes, and a cloud from an eruption of that size does not go where clouds go. Wind is the variable everyone reaches for, and for an ordinary eruption, it is the right one. Material goes up, the wind takes it, and the deposit comes down in a long, tapering fan whose axis points wherever the air happened to be moving that week. Nearly every ash map ever drawn has that shape. Nearly every ash map ever drawn is also of an eruption small enough for the shape to be correct. A column stops climbing at the altitude where the air around it is as light as the column has managed to make itself. Above that height, it would be the denser of the two and would sink back down. Below it, it is buoyant, so it levels off somewhere in the stratosphere and spreads out, and the material arriving from underneath does not stop arriving. There is a second supply feeding the same ceiling. The currents running along the ground are extremely hot, and as they travel, they pull air in across their upper surfaces and heat it, and any part of a current that has taken in enough air becomes lighter than the atmosphere and lifts off. So the flows generate their own plumes along their length and at their edges, and those plumes carry the finest material, the fraction that would otherwise take days to settle, straight up to join what the vent is already delivering. What collects at that ceiling has nowhere left to go except outward. It does what smoke does when it reaches a ceiling, stops rising, then runs sideways along the underside of the layer in every direction at once. The name for the result is an umbrella cloud, which is an unusually literal piece of terminology. The speed at which it runs outward depends on how much material is arriving beneath it, and at the rates involved in an eruption of this class, the spreading is quicker than the wind. That single fact governs everything downstream of it. A cloud expanding outward faster than the air around it is moving does not get carried downwind. It pushes out through the wind in all directions, and the wind is reduced to stretching the resulting circle slightly along one axis. This was worked through properly in 2014 by Larry Mastin and Jacob Lowenstern of the US Geological Survey, together with Alexa Van Eaton, using an ash transport model called ASH 3D. The model had been built for ordinary eruptions and performs well on them, precisely because in ordinary eruptions the wind genuinely is in charge. Running a Yellowstone-scale event through it meant rebuilding the thing to handle an umbrella cloud the width of a continent and to let that cloud act on the wind field rather than simply be carried around by it. What came out was a bullseye. Ash pushed up wind, westward against the prevailing flow, by more than 1,500 kilometers and the same distance north and south, producing lines of equal thickness that come out close to circular and are only secondarily bent by the weather. The deposit sits centered on the volcano rather than trailing away from it. That is not purely a modeling result. Ash carrying the chemical fingerprint of Yellowstone's last caldera eruption has been recovered from seafloor sediments in the Santa Barbara Basin off the coast of Southern California, which is to say west of the volcano and out under the Pacific. The material went upwind 630,000 years ago, and it is still there in the mud, in layers, waiting to be drilled. A circle 1,500 kilometers in radius drawn around northwestern Wyoming encloses something near 7 million square kilometers. The contiguous United States comes to about 8 million, and that is the floor rather than the ceiling of the affected area, because downwind, the ash travels considerably further than 1,500 kilometers. The thicknesses inside that circle are where the story usually goes wrong, so they are worth stating exactly. Across the northern Rocky Mountains, Montana, Idaho, Wyoming, the near field, the model gives decimeters to meters, tens of centimeters at the low end, and in places rather more than a meter. Through the northern Midwest, it drops to centimeters and decimeters. On the eastern seaboard, the west coast, and the Gulf, it comes down to millimeters and centimeters. So if you are somewhere on the Atlantic coast when this happens, what will arrive over the following days and weeks is a dusting. A few millimeters of pale grit on cars, on windowsills, in gutters, drawn into the intakes of air conditioning units. Enough to shut down every airport on the continent, and not by itself, enough to threaten a building. The authors were direct about what their own numbers implied. Their summary states that the ash accumulation, while widespread and substantial, amounts to far less than most of the doomsday scenarios in circulation assume, which is not a minimizing claim, since a meter of ash across the northern Rockies is a regional disaster without any modern precedent, but which does take apart the version in which the country is buried. One caveat belongs with those figures. The model ran a month-long eruption, and a month is longer than some estimates of how long the main phase would go on for. The choice matters, because an eruption lasting weeks experiences weeks of weather, and weeks of weather tend to average toward no particular direction. A shorter, sharper eruption under a steady jet stream would give something more lopsided, considerably worse in one direction and better in the rest. Which direction would be decided by nothing more than the calendar. None of that, though, is what determines whether any particular building is still standing at the end. Ash does not act on continents. It acts on surfaces, on one roof, at one pitch, carrying a load that somebody calculated decades ago from snowfall tables for that county. And ash is not snow. It is powdered rock, several times heavier at the same depth, and it does not go away in the spring. 10 millimeters of ash reached Yakima, Washington in May of 1980. Repairing the city's wastewater treatment plant afterward cost about $4 million. 10 millimeters is a centimeter, less than the depth of a heavy frost from an eruption that would round to nothing against the scale of the one under discussion here. The intuition about ashfall is that damage tracks depth, and that below some obvious threshold nothing much happens. Ash does not work that way, because it does not damage things by burying them. It damages them by being abrasive, by being far heavier than it looks, and by finding its way into openings that were designed with air in mind. Roofs are the clearest case. A pitched timber roof of ordinary domestic construction begins to fail somewhere between 100 and 400 kilograms on every square meter, depending on how it was built and how steeply it slopes. Reinforced structures run higher, from 400 up to 1400. Translated into depth of ash, those loads arrive somewhere between 10 centimeters and a meter, with the low end applying to long-span, low-pitched roofs, the wide, flat-topped buildings, supermarkets and warehouses and sports halls that people tend to gather inside. 100 square meters of roof holding 200 kilograms per square meter is carrying 20 tons. It was not built to. The load is also not fixed, which is the part that catches people. Dry ash and wet ash at the same depth are entirely different weights, because the spaces between the grains fill with water and the water stays there. A roof that comes through the fall itself can go down in the first serious rain afterward, days later, in weather that would be unremarkable on any other week. The same applies to gutters, which were sized for rainwater and are now full of rock. What happened at Yakima is the other half of it. Ash is pulverized rock and volcanic glass, angular at the scale that matters, and inside machinery it behaves like grinding compound. It gets past seals, it takes the faces off pump impellers, it loads motors until they overheat. It settles into sumps and pipework and does not dissolve because there is nothing there for it to dissolve into. A municipal water system is a long chain of pumps and filters and moving parts, every one of them specified on the assumption that what came through would be water and the ordinary things water carries. The same properties apply to the respiratory system, which is also a filter with moving parts. The coarse fraction of ash is caught in the nose and the upper airway and coughed back out, which is what that machinery is for. The fine fraction is not. Particles below roughly 10 micrometers travel past the mechanical defenses into the small airways, and the finest go the whole distance to the alveoli, where the entire design of the lung is to have as little as possible standing between blood and air. Volcanic ash at that size is glass. It is sharp, it does not dissolve, and it does not break down. The body responds with inflammation, which is the correct response, and is also the injury, because inflammation in the deep lung reduces the surface available for getting oxygen across. Breathing is involuntary, and that is the whole of the difficulty. Every other route of exposure can be closed by a decision. You can decline to drink the water, decline to go outside, decline to start the engine. You cannot decline to breathe, and in air carrying a persistent load of fine silicate for weeks on end, the dose accumulates at a rate set by nothing except how long the ash keeps arriving and how hard you are working while it does. For most people, at the depths the modelling gives for anywhere outside the Northern Rockies, the acute effects would be irritation and cough. The serious trouble concentrates among those who already have asthma or chronic lung disease, and among anyone working outdoors, which in the weeks after something like this means everyone doing the clearing. In northeastern Nebraska, the long version has already been written down. The animals in that ash bed did not die of burial. They were standing in the ash and drinking beside it and eating grass through it for weeks. The horses and the camels went first. The rhinoceroses, the largest animals present, lasted longest, and the reason anyone can put a figure on how much longer is a piece of 19th century medicine. In 1890, a French physician named Pierre Marie, working in parallel with the Austrian Eugen von Bamberger, described a condition in living patients with long-standing lung disease. Their bodies had started building fresh bone along the shafts of the limb bones, in places where no bone belongs. Why failing lungs should cause that is still not entirely settled. That they do is not in question, and the process is not quick. It takes weeks of sustained illness to lay down enough of it to be visible. The rhinoceroses at that waterhole have it, not all of them to the same degree, which is itself the useful part, because the quantity varies with how long each animal held on. The bones are a distribution of survival times. Had you been standing in that grassland through those weeks, the hardest thing to credit would have been how ordinary it looked. The grass was still there under the grey. The water was still water. The animals were still walking down to it in the numbers they always walked down in, doing everything they had always done, and every one of them was already past the point where any of it made a difference. Nobody counted those weeks. There was no observer in that grassland with any reason to count, and there would not be one for another 12 million years. The counting was done by the animals themselves, involuntarily, in calcium, as a byproduct of dying slowly. A record kept by the thing being recorded at a resolution no witness could have matched. And it held. The grassland is gone. The climate that grew, it is gone. There are no rhinoceroses in North America now, and have not been for a very long time, and the heat that drove the eruption has moved out from under Idaho and now sits under a different state entirely. What came through all of that is the arithmetic, the number of weeks, still legible in the bone, under a roof in Nebraska, where the skeletons have been left exactly where they lay. That is not consolation. The planet keeps an extraordinary archive, and the archive is indifferent to its contents. It would keep ours on the same terms. There is a question about vocabulary buried in this that has never had a clean answer. The eruption at Bruneau-Jarbidge ran for some number of days or weeks. The ash fell across Nebraska over a comparable stretch. The animals died across the month or two that followed. Somewhere in there, the event ended and the consequences began, and nothing in the rock marks the boundary. We say the eruption killed them, and it is not obvious that the sentence carries a precise meaning. A flow kills in seconds, and nobody would dispute the causation. A lung fails 6 weeks later and 1,000 kilometers away, in an animal that spent those 6 weeks eating and drinking and behaving perfectly normally, and the same verb is being asked to do very different work. The distinction matters more now than it did then, because the interval has been populated. In the Miocene, the weeks between the ash arriving and the animals dying contained nothing but grass and water and a herd going about its business. The equivalent weeks on a modern continent contain hospitals that need power, water that needs pumping, food that needs moving several thousand kilometers, and a few 100 million people making decisions inside a system that none of them can see the whole of. Volcanic ash softens at a temperature lower than the one a jet engine runs at, and that single mismatch is the whole of the aviation problem. Everything else follows from it in a sequence that takes a few seconds to complete. Ash drawn in at the intake goes first through the compressor, where the blades are moving fast enough that pulverized rock behaves as an abrasive and takes material off the leading edges. What survives that arrives in the combustor, which is hotter than the ash's melting point, and the particles stop being particles. The resulting liquid then meets the turbine section immediately downstream, where the blades are deliberately cooled and are therefore the coldest surfaces the melt has encountered since it entered, so it freezes onto them as a glaze, filling the small holes through which cooling air is supposed to escape and narrowing the gap the exhaust has to pass through. Restrict that gap and the airflow through the entire engine backs up. The compressor stalls and the engine goes out. The aggravating detail is that the aircraft cannot see it coming. Weather radar returns echoes from water droplets, which are large and wet and reflective. Ash is dry and fine and returns almost nothing, so a cloud dense enough to end 4 engines can look, from the cockpit, exactly like clear night air. There are documented cases of exactly that, which is why the response in April of 2010 was as sweeping as it was. The eruption that year in Iceland from a volcano whose name most of the world quietly gave up on was small. It was not a caldera event, not a super eruption, not remotely in the class under discussion here. It was a moderate eruption under a glacier in a country that has moderate eruptions with some regularity. European airspace closed for 6 days. Around 100,000 flights were cancelled. Something like 10 million passengers were left where they stood, in the largest disruption to air travel since the Second World War. The airline industry lost roughly $1.7 billion in revenue, against an estimate from its own trade body of $200 million for every day the airspace stayed shut. The instructive part is what came out sideways. More than a fifth of Kenya's economy at the time consisted of flying cut flowers to European markets, and that trade simply stopped. Over 1 million roses were destroyed because there was no way to move them and nowhere for them to go. Bone marrow for transplant patients, which is matched to a specific recipient and has a viability measured in hours, could not be flown from donors in North America to the people waiting for it in Europe. Nobody planning the airspace closure was thinking about roses or marrow. Those are simply things that were riding on aircraft, along with everything else that rides on aircraft, in a system nobody holds a complete picture of. That is the calibration worth carrying forward. Not a prediction of what a Yellowstone eruption would do to aviation. The honest answer is that it would ground flights across most of a hemisphere for a period nobody can specify, but a measurement of how little airborne ash the network tolerates before it stops. The tolerance is essentially zero, and 6 days of one continent cost $1.7 billion. The electrical grid fails by a different route, and a quieter one. Ash on power lines is not the issue. The conductors are bare metal and carry it without complaint. The issue is the insulators, the ceramic or glass stacks that hold energized conductors away from earthed steel. Dry ash sitting on an insulator is a poor conductor and does very little. Wet ash is a good one. So the failures do not arrive with the ashfall. They arrive with the first fog, the first dew, the first light rain, when every coated insulator across a region becomes a partial conductor at once and starts arcing to ground. The remedy is to wash them, which is straightforward and which has to be done individually across tens of thousands of structures by crews who have to drive there through ash on roads with no visible markings, in vehicles whose air filters are clogging. Power is the dependency underneath all the others. Water is pumped, sewage is pumped, fuel is pumped. Cellular networks run on mains power with battery backup measured in hours and generator backup measured in days. Hospitals hold fuel for a defined number of days on the assumption that a tanker will arrive before it runs out, and the tanker route runs over the same roads as everything else. Then there is the sheer physical problem of the material, which is the part that consumes the years. Ash does not decay, drain away, or compact into insignificance. It has to be picked up and carried somewhere, and in the aftermath of a large ashfall, the dominant cost is not repair, but removal, A single suburban roof under 3 centimeters of it is holding a few tons, and that has to come off before the rain by somebody standing on the roof with a shovel, into a container, onto a truck, to a site that has to be found and permitted and is going to fill. Multiply that by every roof, every street, every rail line, every runway, every reservoir and filtration bed across an area the size of a country, and the answer to how long it takes is not a number anyone can give you. It is more than a season. None of that is the part that lasts, though. Roofs get repaired, insulators get washed, airspace reopens by degrees, ash gets moved. The systems described here fail badly, and they fail in ways that are, given enough months and enough money and enough people willing to work in respirators, repairable. The component that does not operate on that schedule left the ground in the first days, went up with everything else, and did not come down. It is not ash, and it is not rock. It is a gas. It is already 30 kilometers above the weather, and by the time the first roof in Nebraska has been cleared, it will have been quietly changing into something else for months. Turning sulfur dioxide into a climate event takes about a month, in 3 stages worth keeping separate. The entire argument lives in the last one. The first stage is placement. Sulfur dioxide released at ground level or anywhere in the lower atmosphere is gone within days. It dissolves into water droplets. The droplets fall as rain, and the sulfur ends up in the soil. That is why ordinary eruptions, however much gas they emit, do not change the climate. The sulfur never gets above the weather. An eruption driving a column 30 kilometers into the air is doing something categorically different. It is placing sulfur into a layer with no rain, no vertical mixing worth the name, and nothing at all to wash it out. Once it is up there, it stays for years, because every route down is slow. The second stage is chemistry. Sulfur dioxide is not itself much of an obstacle to sunlight, being a transparent gas. What matters is that in the stratosphere it reacts, gradually, with water and with hydroxyl radicals and becomes sulfuric acid. And sulfuric acid at those temperatures will not stay a gas. It condenses, along with water, into liquid droplets, an aerosol, a fine acid haze spread across the top of the atmosphere. That conversion takes roughly a month, which is why the cooling after a large eruption does not begin at once and usually peaks the following year. The third stage decides everything, and it has nothing to do with chemistry. It is a question of how large the droplets end up being. A droplet scatters sunlight most efficiently when it is about the size of the wavelength of the light, which is to say a few tenths of a micrometer. Smaller than that, and it barely interacts. Larger, and it still scatters, but the amount of scattering delivered per unit of mass falls away, because mass grows with the cube of the radius, while the cross-section a droplet presents to a beam of light grows only with the square. The everyday version is the difference between fog and drizzle. A cubic meter of air holding a gram of water, as fog is close to opaque, and visibility drops to a few meters. That same gram of water in that same cubic meter divided instead into drizzle leaves the view essentially clear. Identical mass, entirely different outcome, purely as a consequence of how finely it has been split up. A second penalty rides on the first. Larger droplets fall faster, with settling speed rising as the square of the radius. An aerosol made of bigger particles is therefore both less effective while it is aloft and aloft for a shorter time, which brings the difficulty into view. Droplets in a crowded cloud collide and merge, and the rate at which they do so depends on how crowded the cloud is. A modest sulfur injection makes a thin aerosol. The droplets seldom meet, and they stay small and efficient. An enormous injection makes a dense one. The droplets meet constantly, and they grow. The system limits itself. Doubling the sulfur does not double the cooling, because the additional sulfur ends up in bigger, lazier, shorter-lived droplets, and past some point adding more stops buying very much at all. Establishing where that point sits is what Zachary McGraw and colleagues at NASA's Goddard Institute for Space Studies and Columbia University set out to do in a paper published in the Journal of Climate in 2024. They ran super eruptions, defined for their purposes as events discharging more than 1,000 cubic kilometers of magma, which is precisely the lava creek class, through a climate model, across a wide range of assumptions about droplet size, on the grounds that nobody can pin the size down. What came back was a ceiling. Across the cases they examined, global cooling after a super eruption came out at probably no more than 1.5 degrees Celsius, even for the most powerful eruptions simulated. McGraw's remark about the implication is worth quoting exactly. The result could explain why no single super eruption has produced firm evidence of global-scale catastrophe for humans or ecosystems. To get that ceiling into proportion, Pinatubo in 1991 put about 18 megatons of sulfur dioxide into the stratosphere and cooled the planet by roughly 0.7 of a degree, an effect that took 3 years to fade out. Pinatubo was on the order of 1,000 times smaller than the largest eruption Yellowstone has produced. Estimates of the sulfur released by Toba 74,000 years ago run from 70 megatons to more than 6,000, a spread of nearly 100-fold, which is itself a fair statement of how little is known. Take the middle of that range. If cooling scaled with sulfur, the answer would be tens of degrees, and the planet would have been sterilized repeatedly by events it demonstrably came through. The answer is not tens of degrees. It is around twice Pinatubo, for perhaps 100 times the sulfur, all of which rests on a quantity that nobody has measured and nobody can. Droplet size leaves no physical trace. The aerosol falls out, the sulfur is buried in ice and in sediment, and what survives to be sampled is a mass, not a size distribution. Ice cores hold the sulfur faithfully, but blur its timing through mixing and compaction, so even the shape of the deposition curve is uncertain. The one number that decides whether a super eruption is a difficult decade or something far worse is a number the geological record does not carry, and the only route to it runs through models of a process nobody has ever watched at that scale. There is evidence pulling the other way, and it deserves to be put as strongly as the modeling. In the seafloor sediments of the Santa Barbara Basin, the same cores holding Yellowstone ash that traveled west over the Pacific, there are 2 ash layers from the last caldera event, rather than one. They are separated by about 170 years, which means the eruption that produced the caldera people drive through today was, on this reading, 2 eruptions with the better part of 2 centuries between them. Those sediments accumulate finely enough to preserve a year-by-year record, and the temperature of the surface water can be recovered from oxygen isotopes locked into the shells of foraminifera, single-celled organisms that build a shell, die, and settle. After each of the 2 ash layers, that record shows a drop of about 3 degrees. 3 degrees is twice the modelled ceiling, and it is a measurement of something that actually happened rather than a simulation of something that has not. It is also a sea surface temperature in one basin off the coast of California, which is a different quantity from a global average and can swing further than one. Both statements are true simultaneously, and neither disposes of the other. The width of that disagreement is the current state of the field. Nobody involved is being careless. It is a genuinely open question with a factor of 2 or more sitting inside it, and the only way to close it would be to watch the thing happen. What 1.5 degrees would feel like standing outside on an afternoon is nothing whatsoever. It sits well below the threshold at which a body registers a change in temperature, and it is smaller than the difference between one week and the next almost anywhere on Earth. You would not feel a volcanic winter. Nobody has ever felt a global average. A shift of that size is not experienced. It is counted afterward in the places where a small movement in the mean pushes something across a threshold. The date of the last frost, the number of days above the temperature a grain needs to fill, the point at which a growing season is or is not long enough to finish what was planted in it. 1.5 degrees in the global mean is a rearrangement of where the growing seasons are, and it does not arrive evenly. The historical record already contains the demonstration. The eruption that handed Europe and North America the worst summer anyone has written down was not a super eruption, came nowhere near the ceiling described here, and is still remembered by name 2 centuries later. In the summer of 1816, snow fell in New England in June, and the corn froze in the fields before it could ripen. Across the Atlantic that same summer came in as the coldest on record over a span of more than 2 centuries, colder than any year between 1766 and 2000, which is to say colder than every European summer that has ever been properly measured before or since. The particulars are what make the year legible. Farmers planted, the crop came up, the crop was killed, and they planted again with whatever seed was left, and in a great many places that second planting was killed as well. Hay failed, so the animals that would have carried a household through winter were slaughtered early or sold cheap into a market where everyone else was doing the same thing. Grain prices in the affected regions moved by factors that broke households rather than inconveniencing them. The year collected names while it was still going on. The year without a summer, 1800, and froze to death, the poverty year, which is what happens when something is bad enough to need naming and nobody can say what it is. The cause was a mountain in the Indonesian archipelago that almost none of those farmers would ever hear of. Tambora erupted in April of 1815, in the largest eruption documented in the modern era, and the sulfur it delivered to the stratosphere took the better part of a year to finish its work. And here the numbers stop matching the story. The global average temperature in 1816 moved by less than 1 degree, a fraction of the ceiling that the modelling gives for a super eruption, and a change that no person standing outside anywhere on the planet could have detected as temperature. That fraction of 1 degree produced the snow in June, the failed hay, the price of bread, and estimates, necessarily rough, of well over 100,000 deaths from starvation and the diseases that travel with it. The reason a small movement in an average does that much is that agriculture does not respond to averages. It responds to thresholds, and the thresholds are dates. A crop needs a certain number of days between the last frost of spring and the first frost of autumn, and it needs a certain accumulation of warmth inside that window to finish. Both of those are step functions wearing the clothes of continuous ones. A season 1 degree cooler on average does not simply grow slightly less of everything. The frost-free window closes in at both ends, and any crop whose requirement now exceeds that window returns nothing at all, which is a different outcome from returning less. The effect also concentrates itself in precisely the wrong places. It bites at the margins, the high latitudes and the high ground, the regions already sitting close to their own limit, which have historically been the regions feeding themselves locally rather than buying in. 1 degree taken off a growing season in the tropics is a poor year. The same degree taken off at the northern edge of cultivation ends cultivation. If you had been farming in Vermont or in the Vosges through that year, the information available to you was that the crop had frozen twice, that your neighbours had frozen as well, and that nobody could say why. The link between a volcano in the East Indies and a June snowfall in New England was not available to anyone at the time and would not be drawn for a long while afterward. What people had was a year of weather that refused to behave and no framework to put it into. There is a second event in the record that matters more for this argument, and it is smaller again. In June of 1783, a fissure opened in southern Iceland, and stayed open for 8 months. Laki was not a caldera eruption. It produced lava in the ordinary way that Iceland produces lava, out of a crack in the ground, and against the scale under discussion here, it barely registers at all. It released roughly 122 megatons of sulfur dioxide, of which something like 95 reached the lower stratosphere and spread out across the hemisphere. Pinatubo, for comparison, managed 18. A modest fissure eruption in Iceland therefore delivered close to 7 times the sulfur of the largest eruption of the 20th century, because basaltic magma holds a great deal more dissolved sulfur than silica-rich magma does, and Laki was basalt the whole way down. What followed was a haze over Europe that summer, described in a contemporary Icelandic account, in a phrase a recent paper borrowed for its title, as more poison than words can describe. Excess deaths appear in the English and French records through the late summer of 1783 and the winter after it. A 2024 study that reconstructed the likely exposure from meteorological fields concluded carefully that present-day relationships between fine particulate levels and mortality account for only a portion of those deaths, and that the unusually warm summer and the state of 18th century medicine must be carrying the rest, which is a result worth trusting partly because it declines to explain everything. Put the two side by side. Laki produced lava out of a crack in Iceland and put 7 times Pinatubo's sulfur into the air. A Yellowstone caldera eruption would produce on the order of 1,000 cubic kilometers of rhyolite, and how much sulfur comes with that is one of the genuinely open numbers in the whole subject. Volume turns out to be close to irrelevant. The variable is sulfur, and sulfur does not scale with the size of the eruption. It scales with what the magma is made of. Which leaves the question of what a year on the pattern of 1816 would do to a food system that has been rebuilt from the foundations since. Part of the answer is reassuring. Yields per hectare are several times what they were. Grain crosses oceans as a matter of routine. A regional failure in one hemisphere can in principle be covered by a surplus in the other, and has been more than once. The rest is less so. Global food reserves, everything held in store, everywhere, at any given moment, come to somewhere between 4 and 7 months of consumption. Stratospheric aerosol from a large eruption persists for 1 to 3 years. That is the entire arithmetic. The buffer is counted in months, the disturbance is counted in years, and there is no mechanism by which the second becomes shorter. Modelling of what happens to industrial agriculture when the systems underneath it are interrupted – fuel, fertilizer, the grid, the transport that moves all of it – gives yield reductions of 15 to 37% in the first year and 35 to 48% afterward, as the stocks of things manufactured beforehand run down. Those are not by themselves famine figures. A shortfall of 7% in a single major grain is enough to push the global system into crisis, and the countries that come off worst in every model are consistently the ones buying from a narrow set of suppliers while holding small reserves. Those numbers are set down here without a conclusion attached, because the conclusion is not the interesting part, and drawing it is not the job here. The physical chain is what this account is for, and the chain is now complete. Sulfur into the stratosphere, sulfuric acid, droplets, less light, shorter seasons, thresholds crossed at the margins, and a buffer that empties before the aerosol does. None of which is what is happening to the ground. Underneath all of the accounting, the reserves, the shipping, the price of grain in a port 1,000 kilometers from anywhere it was grown, there is ash lying on soil, and soil has no reserves and no suppliers and no shipping season. It has roots in it and burrows under it, and a set of responses to being buried that were worked out a very long time before there was anybody around to write them down. Ecology had a clear expectation about what would be found on the ground inside the blast zone at Mount St. Helens. The expectation was nothing. The model was primary succession, the sequence a landscape follows when it starts from bare mineral substrate with nothing alive in it. Lichens and mosses first, breaking the surface down and contributing the first organic matter. Then grasses and hardy pioneers as something resembling soil begins to accumulate. Then shrubs, and eventually, after a very long time, trees. The sequence had been worked out on glacial forelands and on new lava flows, and everywhere it had been described it was slow. Decades to get anything worth calling a plant community, centuries to get forest. Jerry Franklin, a forest scientist, went in by helicopter about 2 weeks after the eruption of the 18th of May, 1980, and found small plants already pushing up through the ash and animals moving around on the surface. The prediction was not wrong about how primary succession works. The mistake was in the classification. This was not a landscape starting from nothing. The idea that came out of the decades afterward is called biological legacies, and it is one of those concepts that sounds obvious the moment somebody says it aloud. A disturbance, however severe, does not clear a site. It kills most of what was there and leaves the remainder, and the remainder is not randomly distributed. It is whatever happened to occupy a position the disturbance could not reach. Seeds in the soil, roots below the killing depth, standing dead wood, already dead and therefore unkillable. Organic matter buried underneath the new deposit, and animals that were, at the relevant moment, underground. The northern pocket gopher is a small burrowing rodent that spends effectively its whole life below the surface, eating roots, and it was in its burrow on the morning of the 18th of May. The lateral blast took the forest off the landscape above it. The blast did not get more than a few tens of centimeters into the ground, because ordinary soil is an excellent insulator and a poor conductor of a shockwave, and the gophers came through in numbers. What they did next is the part that matters. A gopher digging in ash does what a gopher always does, which is push its spoil up to the surface. And the spoil in this case was the buried forest soil from beneath the new deposit, carrying organic matter, fungal networks, seeds, and the bacteria that make nitrogen available to roots. Every burrow entrance became a small heap of living soil sitting on top of sterile pomace. The animals were not recolonizing the site. Without any intention in the matter whatsoever, they were reversing the burial from underneath, one heap at a time, across the entire area they occupied. The arrivals from outside were stranger. Among the earliest colonizers to reach the deposit were spiders carried in on strands of silk, ballooning, which is a real dispersal strategy rather than an accident, and which drops very large numbers of very small spiders onto any downwind surface. They landed on a plain of hot pumice with nothing at all to eat, and most of them died where they landed. That turned out to be their contribution. A dead spider is nitrogen and carbon delivered onto a surface that had neither at a steady rate for years. And then there were the lupines, which are the reason any of it moved as quickly as it did. Lupines are legumes, and legumes carry bacteria in nodules on their roots that convert nitrogen gas straight out of the air into a form a plant can use. Nitrogen is almost always the limiting nutrient on fresh volcanic ground. Rock supplies plenty of phosphorus and potassium and the rest, and essentially no nitrogen, because nitrogen enters an ecosystem biologically rather than geologically. A lupine growing on bare pumice is not waiting for soil to arrive. It is manufacturing the one ingredient pumice cannot provide out of the atmosphere and leaving it in the ground when it dies. The recovery has not been even, and the unevenness is where the information is. The northwestern quadrant of the blast zone, furthest from the volcano, was showing visible green by the late 1980s. The ground east of Spirit Lake stayed largely bare for another decade after that. Same eruption, same year, same climate, different legacies, different distances, and different depths of snow still lying on the ground that morning, which in places was precisely the difference between a plant surviving and a plant not. The eruption itself occupied a single morning and has been picked over more thoroughly than almost any geological event on record. The recovery has been running for 45 years, and it is where essentially all of the transferable knowledge came from: how disturbed systems actually reassemble, what sets the rate, which interventions help and which get in the way. It is also the part nobody films. There is no dramatic footage of a lupine. The scientists who flew in 2 weeks afterward have retired, and the long-term measurements are now being taken by people who had not been born when the mountain came apart. There is a larger version of this, and it involves people. The Toba eruption in Sumatra, about 74,000 years ago, was several times the size of anything Yellowstone has produced, and for a long stretch, the standard account held that the volcanic winter afterward cut the human population to a few thousand individuals, a genetic bottleneck from which everyone now alive is descended. It was a memorable story, and it turned up in a great many places. The evidence has gone the other way. Sediment cores from Lake Malawi in East Africa contain the Toba ash as a layer of microscopic glass, and the same cores carry a continuous record of vegetation and lake ecology sampled at intervals of a few millimeters, which is to say at a resolution of years. Across the ash layer, and for centuries on either side of it, tree cover does not change. Grass abundance does not change. The algae and the midges and the diatoms, which react quickly to temperature and to mixing, never leave their ordinary range. There is no 6-year volcanic winter in that record because there does not appear to have been one there to record. The archaeology has gone further. Toba's ash can now be identified at sites where no visible layer exists at all, by separating individual glass shards out of the sediment under a microscope with a fine manipulator and matching their chemistry against the eruption, which means particular occupation flaws can be dated directly against it. At Pinnacle Point on the South African coast, human activity increases after the ash arrives and new tool technologies appear. At a site in Ethiopia, people shift their subsistence towards seasonal rivers and shrinking waterholes and take up the bow and arrow. Those are not the traces of a population barely holding on. They are the traces of a population doing the thing that population has always been distinguished by, which is altering its behavior faster than the environment can alter underneath it. The blast zone today is difficult to read as a blast zone. You would want it pointed out to you. The young conifers standing across most of it, the elk, the grey trunks that survived by having already been dead, the lake full of fish again. What is not visible, and what took 45 years of people going back with the same instruments to establish, is that hardly any of it arrived from somewhere else. Most of it had been there the entire time, a few tens of centimetres down, waiting for a gopher. Mount St. Helens removed something on the order of a cubic kilometre. The system under Yellowstone has, 3 times now, removed a great deal more than that, and on none of those occasions did the hole it left stay a hole. 630,000 years is enough time for a caldera to stop looking like one. The one under northwestern Wyoming cannot be seen from inside it, which was the entire difficulty in recognizing it, and it cannot be made out from most of the roads that cross it either. There is no rim worth the name at the places where people pull over. What there is instead is a broad forested plateau standing high above the country around it, with a very large lake in its southeastern quarter, canyons cut into its edges, steam rising out of the ground in patches, and nothing about it that reads as the floor of a hole. Whatever the system does next, you will not see it, and neither will anyone you are ever going to meet. The intervals here are long enough that a human lifetime is not a unit this place operates in. the whole of recorded history is shorter than the uncertainty attached to most of the dates involved. What happens to a hole of that size once the eruption stops is that it begins filling from several directions at once, and the first contribution is the eruption's own. A great deal of what comes out lands back inside the ring, and it lands hot and it welds itself together, which is why the tuff inside a caldera is measured in kilometers of thickness, while the identical rock a few kilometers outside is measured in tens of meters. Before anything else has happened, the hole is already substantially full of itself. Then the water. A collapsed caldera has no outlet until erosion cuts one, so precipitation gathers in the low ground and the depression becomes a lake. Yellowstone Lake sits on part of that floor today, and its abandoned shorelines, stranded at different heights around the basin, hold a record of the caldera moving up and down across the last several thousand years, a ledger of inflation and deflation, written by water repeatedly finding its level against a floor that would not stay put. The floor will not stay put because the magma underneath it did not all leave. What remained repressurizes as it cools and crystallizes and gives up its gas, and it pushes the caldera floor back upward from below. The two places where this has gone furthest are known as the Sour Creek and Mallard Lake domes, and between them they have raised a considerable portion of the caldera floor back toward the elevation it started from. A caldera does not stay a depression. It begins recovering its height almost at once, from underneath, on a schedule of tens of thousands of years. The largest contribution of all is lava. Between roughly 180,000 and 70,000 years ago, about 600 cubic kilometers of rhyolite came up inside the caldera and spread across the floor as thick, slow flows. Not explosive eruptions in any sense, simply enormous quantities of extremely viscous rock emerging and going nowhere in a hurry. Spread across the caldera floor, that volume comes to a couple of 100 meters of new ground. They arrived at intervals. Across the stretch from about 160,000 years ago to about 70,000, the rate works out at one flow every 20,000 years or so. The Nez Perce Creek flow at around 160,000. The West Yellowstone flow at 110, and then the Pitchstone Plateau in the southwestern corner of the park at roughly 70,000 years, the largest of them and the last, and now a quiet forested upland that hardly anybody walks across and nothing whatsoever marks. For a long time, that was where the eruptive record stopped. It moved in 2025. New argon dating by Cole Messer, Kenneth Sims and colleagues, published in Geology, brought a basalt flow near the Henry's Fork caldera, west of the park, outside the present caldera, down to about 35,000 years, which makes it the youngest known Yellowstone eruption of any kind. Previous work had put the youngest basalt out there at something closer to 120,000. The same study turned up something more useful than a revised date. Basaltic eruptions outside the caldera cluster in time with the great rhyolitic eruptions inside it, and the reading the authors offer is that the basalt has been thermally priming the whole apparatus, delivering heat upward into the crust, keeping the silicic reservoir hot enough to remain a reservoir. Why the basalt erupts around the outside rather than through the middle is straightforward once stated. Rhyolite is less dense, and a body of it sitting in the upper crust functions as a lid that denser basalt cannot push through. So the basalt goes around the edges and comes up where the lid is not, which means the deep part of the system has not been idle during the 70,000 years the shallow part has been silent. The electrical imaging points somewhere compatible and adds a geography to it. The western side of the system appears to be winding down, and the melt still connected to deeper supply is sitting in the northeast. If Yellowstone does anything at all in the next stretch, the current best guess about where does not put it in the middle of the park. all of which raises a question about the word that gets used for this place. Yellowstone has produced 3 caldera-forming eruptions in 2.1 million years. Across the same interval, it has produced something on the order of 80 separate lava flows, an unbroken hydrothermal system, and an essentially continuous supply of earthquakes. If the behavior of this volcano was sampled at random from across its history, the chance of landing on one of the 3 events that made its reputation would be very small. Supervolcano is not a wrong word. It names something real, and the something real is the worst thing this system does. It has also organized public understanding of an entire region around that system's rarest behavior, in roughly the way a river is not well described by its floods, even though the floods are what matter on the days they happen. There is no monument on the Pitchstone Plateau, and nothing to put one on. The last caldera eruption left behind a plateau, a lake, 2 low domes, and a great deal of pleasant country, none of which carries any record a person could read without instruments. Several million people a year drive across the floor of it, and virtually none of them are conscious of standing on a disaster site, because it does not look like one, and has not looked like one for a very long time. Nothing there is keeping the record. The place has simply gone on accumulating. One number in all of this refuses to sit quietly with the others. From 160,000 years ago to 70,000, the lava flows came at roughly 20,000-year intervals. Nothing rhyolitic has come out for 70,000 years, which is 3.5 times that spacing. There are 2 ways to read that, and they point in opposite directions. One is that the system is winding down, which is broadly what the imaging of the remaining melt would suggest. The other is the reading that has done more damage to the public understanding of this place than any other single idea in circulation, and it deserves to be dismantled carefully rather than simply dismissed. The volcano is doing tonight what it does most nights. Steam is lifting off the geyser basins into cold air. The ground across the caldera sits a couple of centimeters lower than it did 12 months ago and is still going down. Small earthquakes are working their way through the fractured rock the way they do every month, and nobody will feel any of them. By every measure anyone has, it is an ordinary night on an ordinary volcano, and it has been an ordinary night for 70,000 years. The claim that it is overdue deserves taking apart carefully, because it is not simply wrong. It is wrong in a way that can be checked in half a minute, using the numbers the claim itself supplies. 3 caldera-forming eruptions, 2.1 million years ago, 1.3 million, and 640,000. That gives 2 intervals, 800,000 years and 660,000. Average them, and the answer is 730,000 years. The last eruption was 640,000 years ago, which means that on the arithmetic being invoked, the next one is not due for another 90,000 years. That is the shallow objection, and it is sufficient by itself. The deeper one is that 2 intervals is not a sample. 2 numbers cannot establish a distribution, cannot yield a variance, and cannot support the word average doing any real work. It is the same reasoning as tossing a coin 3 times, getting 2 heads, and announcing that tails is now due. And the 3 events may not be 3. The oldest was erupted in at least 2 separate episodes spread across some 20,000 years, with the Earth's magnetic field reversing partway through. The most recent, on the evidence recovered from the seafloor off California, may itself have been 2 eruptions 170 years apart. If these events are clusters rather than points, the intervals were never intervals, and the arithmetic was never measuring the thing it claimed to measure. What can be said about likelihood comes out very small and reasonably firm. The US Geological Survey puts the annual probability of a volcanic eruption at Yellowstone, any eruption, not specifically a caldera-forming one, at around 1 in 100,000. Across an 80-year life, yours for instance, that works out to roughly one chance in 1200. Across the entire span of written human history, 5,000 years or thereabouts, it comes to about 1 in 20. And it did not happen. The survey attaches a caveat to its own figure that is more interesting than the figure. Even 1 in 100,000, they note, is probably an overestimate for the short term. The reasoning is that a base rate computed across the whole history of a system assumes the present moment is a random draw from that history, and the present moment is not. The melt is dispersed well below the fraction at which it could move. The gas is leaving as fast as it accumulates. The ground is going down. The more useful question is not whether Yellowstone will erupt, it is what, in that region, has actually harmed anybody. At the top of the list is hot water. Hydrothermal explosions are the most common geological hazard in the park by an enormous margin. They occur on timescales of years and decades rather than hundreds of thousands of years. They have left craters around the lakeshore large enough to form bays in it, and one of them destroyed a boardwalk in front of visitors on a July morning in 2024, then did it again a few weeks later. Below that, and considerably more lethal, are earthquakes. On the 17th of August 1959, at 20 minutes to midnight, a magnitude 7.3 earthquake struck about 10 kilometers west of the park boundary near Hebgen Lake. The fault scarps it left at the surface stand 5 or 6 meters high in places. It shook close to 40 million cubic meters of rock off the wall of the Madison Canyon. The slide ran down one side and partway up the other, dammed the river, and created a lake that is still there and is still called Earthquake Lake. 28 people died, most of them in a campground beneath the slope. The survey's own statement of the hazard ordering is blunt about it. The hazard and the risk from large earthquakes is far greater than from any volcanic eruption, for the straightforward reason that earthquakes happen so much more often. What cannot be said is a shorter list than it once was, and it still holds 3 items that matter. The first is the droplet size that decides whether a supereruption is a difficult decade or something categorically worse. It leaves no physical trace anywhere, and the honest position is that the answer is modelled rather than known. The second is the reach of the flows. There is still no published hazard model for pyroclastic currents from particular vents in that caldera, and there will not be one until somebody decides a low-probability event deserves that kind of computational effort. The third is larger than either, and it reopened 4 months ago. For most of the last half-century, the standard account placed Yellowstone above a mantle plume, a narrow column of hot material rising from the boundary between the Earth's core and its mantle, nearly 3,000 kilometers down, with the continent sliding across the top of it. In 2018, seismic waves that had traveled through the core were used to image something answering that description. A slow, roughly cylindrical anomaly, some 350 kilometers across, tilted northeast, extending the full depth of the mantle. In April of 2026, a paper in Science by Zebin Kao, Lijun Liu and colleagues argued that the magma plumbing beneath Yellowstone is governed by the mechanics of the plate itself, by the weight distribution within the lithosphere, and by the drag of asthenosphere flowing eastward underneath it, with what the authors call a negligible contribution from any deep plume. On that reading, the heat is arriving from much shallower, and the plume is not the explanation for any of it. That argument is 4 months old and nowhere near settled, which means the most intensively studied volcanic system on the planet, ringed by more instruments than almost anything else in geology, is currently the subject of an open dispute about where its heat comes from. Set against all of that, the thing most worth carrying away is the shape of the record rather than any single number inside it. Yellowstone has existed as a volcanic center for a little over 2 million years. In that time, it has produced 3 caldera-forming eruptions and something on the order of 80 lava flows, and it has spent the overwhelming majority of the interval doing precisely what it is doing tonight. Moving heat through hot water, rising and settling by centimeters, generating earthquakes nobody notices. It would be natural to call the quiet the gap between the eruptions. The proportions run the other way. The quiet is what this system is, and the 3 events are interruptions of it, brief ones at the scale the rock keeps. There were hominins on the African savanna during all 3. Nobody was in North America for any of them. The species that eventually built the instruments now sitting on that caldera did not exist for the first 2 and had not yet appeared for the 3rd, and the lineage that leads to the people studying the place came through every one of them from a very great distance. And after each event, the interval. Hydrothermal systems reassembling over thousands of years. Lava filling the hole back in over tens of thousands more. A lake forming and stranding its old shorelines as the floor rose underneath it. Forest returning to a plateau that had been sterilized by exactly the mechanisms that returned forest to a mountain in Washington across the last 45 years, on a longer clock and with nobody present to write any of it down. The long quiet is the part that lasts. It is also the part with no images attached to it, which is very nearly the whole reason nobody has heard of it. There is a particular calm available in this material, and it is worth being exact about what it is made of. It is not safety. 1 in 100,000 a year is a small number, and it is not 0, and it feels small largely because a year is a small unit. Stretch the unit, and the number stops being small. Stretch it far enough, and it stops being uncertain. It is not a promise that people would come through it either. The record shows populations under great pressure repeatedly doing things that look, from a distance, like resilience, the new tools appearing at pinnacle point after the ash, the bow and arrow at the Ethiopian site, the Gopher pushing living soil up through a meter of dead pumice. None of that was resilience in any sense the animals involved would have recognized. It was ordinary behavior, carried out by whatever happened to be positioned to keep carrying it out. What is on offer is proportion. The animals in that Nebraska waterhole did not survive. What survived was the count of their weeks, written in calcium, indifferent to whether anyone would ever read it. The planet keeps an excellent archive and holds no opinion about the contents. It will keep this century on the same terms, at the same resolution, and it will not be keeping it for us. That is not comfort, and it was never offered as any. It is proportion, and proportion was the thing that was actually missing. So, the reckoning, in order. Yellowstone is not overdue, and the arithmetic used to say so has been done wrong by the people using it. The annual probability is around 1 in 100,000 and is probably lower than that at present. The melt below is dispersed. The gas is leaving. The most likely eruption, if one comes, is a lava flow, and the most likely hazard is hot water. The most dangerous thing in that region, on the evidence of the last century, was an earthquake at 20 to midnight in August. And if the caldera did go, the 4 days, the column, the collapse, all of it, the flows would cover less ground than the park does. The ash would fall in a circle rather than a plume, and across most of the continent it would be measured in millimeters. The cooling would probably not exceed 1.5 degrees, and 1.5 degrees would still be enough to take the summer away from the margins for 2 or 3 years running. None of that is nothing. All of it is smaller than the story. The long winter on that plateau is the one that arrives every year. It comes in October and does not leave until May. It buries the roads. It lays a meter of snow over ground that is warm underneath, so the thermal basins stand out as bare dark patches steaming in a white field, and the weight of all that water soaking down through fractured rock as it melts is enough to make the entire caldera pause its slow settling for a few months every summer before it resumes. That is the long winter here, The ordinary one, arriving on schedule, doing its small, measurable work on a system otherwise indifferent to everything. It is probably snowing up there now. The instruments are recording, the ground is going down by 2 or 3 centimeters a year and has been for a decade, and will keep going down tonight and tomorrow and through the rest of the week. Nothing is happening. That is not a failure of the monitoring. That is the finding. Whatever you brought into this, the number you had in your head about that place, the shape of the thing you thought was waiting under it, you can put it down now. It is a volcano. It is a very large one. It is quiet, in the specific sense that the physics is not currently arranged for it to be anything else. The ground is settling, slowly. A couple of centimeters a year, the way it has been settling since before you were born, and the way it will most likely still be settling a long time after. Nothing out there needs you tonight. Good night.